Welcome to the second module of the CFD course. In this module we are going to look at the equations which describe fluid motion. This is an important aspect of CFD because we are trying to solve the equations numerically and we have to make sure that we are solving the correct equations, the equations which represent the physics of the problem. There is another aspect to the solution of equations using CFD in the sense that when we are looking at analytical solutions we may have to make certain simplifying assumptions, but when we are doing numerical solution then those simplifying assumptions need not be made. For example, if you look at for example the viscosity variation with temperature, only certain types of certain forms of certain analytical forms, for example the exponential form may be something that would yield us an analytical solution, whereas in while dealing with a numerical solution we are not necessarily restricted to the exponential form, we can bring in any other form. And it is also possible that along with fluid flow there are a number of other phenomena that are happening and these need to be represented mathematically, and that is possible in CFD. It is possible to solve these equations together with other equations in CFD, and we often make use of this facility to deal with practical problems. For example, turbulent flow or a flow with turbulent flow with reaction or a two-phase flow. In all these cases we have an extended set of equations, and it is this extended set of equations that we are trying to solve, and we have to see that this set of equations that we are trying to solve is correct, and it takes advantage of the facility that is offered by CFD, which is that we can solve many more cases, many more different types of equations than what is possible analytically. So it is in that sense we have to look at a problem formulation, mathematical formulation, which is the most generic possible. So that is one of the things, and which is why the equations that we solve in CFD are not like the Biphenyls equation, or not like one-dimensional equations. It is the general three-dimensional unsteady equation set of equations which describe fluid motion, and we would like to look at those equations and what they mean and how to mathematically pose the problem in such a way that we can then attempt a CFD solution. We can piece together a format for discretizing these things and then converting these into algebraic equations and solve that. So that is the essence of this particular module. What are the equations which govern fluid motion in the most generic case, and in that general case we would like to take those equations and then do the discretization, so that by changing the flow domain we can apply these to different cases. For example, the equations which would describe the flow through a rectangular duct are the same as the equations that would describe the flow through a triangular duct or maybe unsteady flow. So those are the kind of general case equations that we would like to derive here. So when we look at the equations which would describe motion of fluids, then there is no reason to disbelieve that the equations of motion that we have for solids are not applicable for liquids or gases. Okay, so in that sense we are still looking at the basic framework of equations which we are familiar with for solid mechanics. For example, we are expecting in a fluid flow for certain fundamental laws to be upheld, which is conservation of mass, conservation of linear momentum, conservation of energy, and for fluids we have special kind of things that are coming here, the equation of state and also the boundary conditions and initial conditions. So these are the ones which together make up the mathematical formulation, and it is these equations that we are going to derive in this particular module. So, in the first module we will be looking at the first two equations along with some basic introduction about fluids, and in the second module we will be looking at the other part of the outline here. So, let us first of all establish the difference between fluids and solids. Okay, we have an instinctive feel for what fluids are and what solids are, but in a technical way we can say that fluids are those physical substances which cannot withstand shear stress, and by this we mean that they cannot withstand means that they deform continuously, that is the deformation continues as long as the stress is applied, unlike the case of a solid which deforms. It also deforms upon the application of shear stress, but it soon reaches a condition of equilibrium between the force that is applied, the shear stress that is applied, and the internal resistive force that is generated, so as to reach a shape which is unchanging with further passage of time. Whereas in the case of liquids as shown in this slide here, if you consider an initially rectangular fluid element, so by this we can mark it as, we can mark point ABCD within the fluid continuum, and these are such that these are separated in the fluid in such a way that if you draw straight lines through them you will have a rectangle at time equal to 0 at when you start observing this, and with time they are flowing, so that is they are moving along, and then if you apply the shear stress, then A is coming here and B is coming here and C is coming here, D is coming here, and in such a way that now if you join them by straight lines you get a shape which is like a parallelogram as shown here for a small time, and then after some more time this parallelogram is more distorted and even more distorted and so on. So, in the case of fluid, the initial rectangle keeps deforming continuously with time, it does not stop, whereas in the case of a solid, once it reaches a certain level of deformation like in the second picture here, then there is already a resistive force which is generated internally, which will eventually reach an equilibrium with the applied stress, so as to maintain a shape in this distorted fashion. So, it is this nature of fluids that they continue to deform with the application of shear stress that differentiates fluids from solids, and both liquids and gases they exhibit this kind of behavior. Okay. So, we can say that liquids and gases are fluids, and in a sense they flow, they start moving relative to each other upon the application of a shear stress. One of the differences is liquids are nearly incompressible while gases are highly compressible, and there is also, in contrast to solids are essentially fixed in their arrays or in their relative position to each other, and they remain fixed. In the case of liquids, they go around, they move around within that liquid continuum, but they cannot go everywhere. There is an interface which is separating the liquid from the gas phase. In the case of gases, there is no such interface, and the gas molecules are free to move around in the whole available continuum until they are blocked by an impermeable wall or an impermeable liquid surface. So, gas molecules will tend to occupy the available volume over a period of time, whereas liquid will retain its volume, but it may change its shape depending on the forces that are acting on it, and a solid will retain its shape and volume with passage of time unless there are some special forces acting on it. So, if you want to look at the distinction between these, since you are all students, you can consider the students in a primary school. The kids stay in the classroom, and then the teacher comes out and every period the teacher comes out, and then a new teacher comes in, new subject is taught, like that, they sit in the seats most of the time. Liquids are like college students. Okay, you are going from one course to another course, maybe you are changing your rooms, maybe you are going into a different labs, but the batch as a whole retains its cohesiveness. So it's unless somebody fails or gets suspended, okay, or has some other problem, the batch remains the same, but they are not fixed, they are not there all the time in their classrooms. So they don't retain that particular shape that a set of school students, primary school students have. Okay. Now if you go to even higher studies, then or maybe in your 4th year and final years and pre-final years, when you start taking electives, then the cohesiveness of the batch also gets lost, because some students may be taking this elective, some students may be taking some other elective, some students may be doing a semester in some other institute kind of program. So it is no longer they are no longer confined to that school compound, they are everywhere, they can be everywhere. Okay. So in that sense, and what is making the difference between a primary school and first or second year bachelor's program and then senior years and all that, it is the freedom that is there, the maturity that is there within you, which allows you to be given that freedom to go around and move around and still be safe and responsible. So in the same way, as you increase the energy of the substance, you go from solids to fluids, solids to liquids to gaseous state. We are dealing with not those energies, we are dealing with essentially fluids and how they flow and what is the effect of the flow. Okay. Now we would like to make a distinction between liquids and gases, and we would like to point out at this stage that the fluids have a couple of special properties that solids do not have. One is the concept of pressure. Okay. So you can visualize an imaginary plane which is put in the liquid continuum, and the liquid molecules are free to go around this way, that way in random directions, and therefore some of them will be hitting the wall, hitting this imaginary surface, and then so that will give rise to a potential exchange of momentum, and that can be considered as an equivalent to a pressure. Okay. So fluid molecules will exert pressure on an imaginary surface which is present in the continuum, and this gives rise to the concept of pressure, and the pressure is always compressive stress which is there, which is normal to a surface immersed in that fluid, whether it is a gas or a liquid. The other important property about fluids is the concept of viscosity. Okay. So fluids are not like a plasma or something like that, they still resist relative motion, in the sense that if you have a fluid molecule and then if it is going to be dragged away by the applied shear force, then there is some kind of cohesive force which is trying to resist this, and the layers which are the fluid molecules and the layers below that will try to resist this and set up a resistive force. So this means that if you want to create a velocity gradient and then if you want to maintain it, you need to do some work, and all this gets translated into the property of viscosity, and we will see a bit more about this, but there is a property of viscosity which is similar to the property of elasticity that is present in solids, whereas in solids the stress and the deformation that are produced are proportional to each other. Here it is the stress and the rate of deformation that is produced, and this relation between the two is expressed in the form of viscosity. So viscosity is a property that is present in fluids, both gases and liquids, and liquids have one more special property, which is the interfacial tension or a surface tension. The surface between a solid and a liquid or between a gas and a liquid is a special kind of surface, and there is effectively a surface tension which acts as a force on that. It arises in some special cases, definitely very important in some industrial contexts, but usually in our regular fluid mechanics we neglect that, so we do not go too much into that, but it is an extra thing that can be added to the set of governing equations which we are going to describe, which we are going to discuss in the next classes. Okay. So, in this course we are not going to deal with surface tension, so that is left out of the forces that we are going to deal with. So, we understand the major differences between solid and fluid and gases, and what we have done is just to recap those things, and we need to keep these ideas in mind when we discuss the governing equations. Okay. So, when we talk about the governing equations, we already mentioned certain fundamental laws which must be obeyed by all substances, and fluids while they are flowing must also satisfy these laws, and one of these, the most basic of this, is the conservation of mass. In the absence of nuclear reactions, which is what we are considering, we expect the conservation of mass to be upheld while the fluid is flowing. Okay. So, conservation of mass can be represented mathematically as dm by dt equal to 0, but when we are dealing with fluids, we are at some disadvantage compared to when we are dealing with solids, because in a solid it is easy to identify a system, it is easy to identify what are the molecules or what are the particles of the solid that we are dealing with, like a motor car. Okay. So, the motor car is a system which is comprised of the passengers inside, and then it has a definite shape, it is in a bounded volume which is moving along because you are applying some force through the motor, and then there are some viscous forces, wall friction, tire friction, and then air drag, and all those things are there, and based on this you can describe the velocity or the change of velocity of that vehicle, and all the time you are looking at the same set of people and the same set of tires and the same set of motor vehicle molecules and particles that are there. In the case of fluid flow, it is not really easy to keep track of the ever changing shape of the liquid in case of liquids, and in the case of gases they do not have a shape. It is difficult to keep track of the individual gaseous particles that are present. So, we always talk in terms of, for fluids, we talk in terms of the changes that are happening in a fixed or a moving control volume. Okay. Like we are looking at for example, within the motor car, we could be looking at the way that the cold air is coming through the air conditioning system and then it is spreading. So, we are not looking at the individual molecule of the air, but we are looking at what is the flow of air and how is it spreading its coldness and how is it getting hot, because the hot air because they are exchanging heat with the passenger sitting inside, and then so what is the temperature field, what is the velocity field, who gets the coldest air first, and what is the flow pattern. So, these are all we are talking about what is happening inside the car, and that is what is of interest. If you are looking at a chemical reactor, usually these are maybe some stirred vessel with some reactant coming in and another reactant being fed and some reaction going on like this. Again, you are looking at how does the concentration change and how do the reactants mix, where do the products go, and so this type of thing you are concentrating on what is happening inside that reactor. So, we are always looking at what is happening inside a control volume rather than asking what is happening to this particular particle, and these two are equivalent. Okay. Again, coming back to the educational example, one can learn about the system of knowledge sharing, knowledge giving that is happening in an engineering program by tracking the increasing level of knowledge of a student as he or she goes through the bachelor's program. If you have some way of measuring what is the knowledge in a particular domain, and then if you start measuring it at the time of entry and every month after entry as the student is going through the classes, then you can do that, and then you can do that for hundreds of students and get to know what is the knowledge transfer process that is happening in this particular program. Or you can look at a classroom and then you can see over a period of time what kind of knowledge exchange is taking place inside the classroom, and then how the students are benefiting, and then you do it for all the different classrooms in which different subjects are being taught, and then you can get an idea of the knowledge transfer process. So both of them, if they are done very accurately, will give us the same information, but which we do depends on a convenience. Okay. In the case of, for example, if you are looking at a specific subject and if you are looking at CFD and how it is, what kind of knowledge transfer is taking place in CFD, then we would like to look at a classroom and then we would look at what is happening inside, what is the topic that is being discussed today and what is the next one and all that. So we are looking at a particular classroom and then see what is happening. We are not looking at a sample of students who are being sampled every day, and that is the kind of control volume kind of formulation that we do for fluids purely for the sake of convenience. And we look at that kind of formulation to describe mathematically these fundamental laws of conservation of mass, momentum and energy, so that we can get some equations out of this. So one application of the conservation of mass is what is shown in the slide here. We have here conveniently chosen cubical control volume with origin right here at the back side, and then x going in the horizontal right side direction, y going in the vertical upward direction, and since we follow the right hand coordinate system, z is coming out towards us. So that is the direction, that is a coordinate system, and this particular box here has a length of delta x in the x direction, a length of delta y in the y direction, and length of delta z in the z direction. So this is our box and our control volume, and within this we would like to describe in simple verbal statement this conservation of mass. Okay. So we can describe it as rate of accumulation of mass within the control volume is equal to rate at which mass enters the control volume and rate at which it leaves the control volume. So why do we talk about entering and leaving? This particular volume, where is it? It is a small portion in a fluid continuum. So in this room there is a box here, and within this I am looking at what is coming in, what is going out. And why is it coming in? Because there is flow. There is flow coming in like this and there is flow coming in like this from all sides. There may be flow like this. So it is coming in through some, it is coming into the control volume and then it is going out through the control volume. And in the process there are changes, there can be changes, and it is those changes that we are looking at. And what we are saying is that as the fluid is flowing through, there can be changes, but those changes will have to obey the conservation of mass. And what that conservation of mass is, that the rate of accumulation of mass within the control volume is the rate at which it enters the control volume minus the rate at which it leaves the control volume. If there is a difference between the two, then there is a rate of accumulation. If what is leaving is greater than what is coming in, then it is a rate of decrease of mass within the control volume. Okay. If the rate at which it enters is more, then there will be rate of accumulation. So depending on whichever is greater, the rate of accumulation can be negative or positive. So we can describe this mass here using the concept of density, and so we know that density times volume is the mass, and we are therefore saying that the density of the fluid in this location, okay, maybe at the center of this or integrated over this entire volume, is times the volume, which is delta x, delta y, delta z, is the total mass, and rate of change of this with time can be represented as partial derivative of dou by dou t of rho delta x, delta y, delta z. So this is a statement of the rate of accumulation, a mathematical representation of this. Now we need to find out the rate at which the fluid enters and then rate at which it leaves. If you take a surface here, for example this face here at this point, then the mass flow rate through that surface is given by rho u dot A, okay, rho u dA, which is integrated over the entire surface here. So here this is a dot product, so that is if the velocity is at an angle to this, then there is less flow which is entering, and as if the velocity is parallel to this face, then it cannot be entering the control volume. Okay, so that is why we take a dot product between the outward normal vector of the face, which is A here, and then the velocity which has a certain orientation. So now we have chosen these faces in a convenient way. We have chosen this, if you consider this block, this box here, it has a left face and a right face, a top face and a bottom face, a front face which is this one, and a back face, and these are oriented in the corresponding xyz coordinate system. Okay. So that means that the outward normal vectors for each of these faces is aligned either in the x direction or y direction or z direction. Okay. So that means that we need to multiply only by the corresponding velocity component here in order to get this. For example, if you look at this one here, if you look at the left face, this is the face, we are assuming that u has components u, v, w, and these are positive, so that if you have a u here, then that is aligned in the x direction, so that means it will be entering. Here on the right face, if there is a u, then it is again aligned in the x direction, positive x direction, so it will be leaving the surface. So you can say that through the left face and through the bottom face and through the back face, flow is entering, and through the right face and through the top face and through the front face, the fluid is going out. So you can put it like this, or you can strictly apply the dot product and then get the same values here. So we can say that the total flow rate that is entering, the mass flow rate, is the density times the x velocity component, which is u, times the area of the left face, which is delta y times delta z. Okay. And this is evaluated at x, at this particular point here, which is at x and mid y and mid z here. And through the bottom face, you have a corresponding velocity which is perpendicular to the face direction, is v. So rho v times the area of this face, which is delta z times delta x, is the total flow rate, mass flow rate, that is coming in through the bottom face. Similarly, through the back face, it is the w velocity component at the midpoint of this face at a z location of z here is so that velocity w times the area of this face, which is delta x times delta y, will give you the total flow rate that is coming in. Okay. So similarly, we can say, we can evaluate the mass flow rate out, which is rho u times delta y delta z at x plus dx, because this face is at a location of x plus delta x here. So the velocity at this point, that is at a point of x plus delta x, can be different from velocity at x because of the changes that are taking place inside the control volume. If that is the case, then the flow rate that is going out has a velocity of u at x plus delta x, and this u at x plus delta x can be different from u. If it is different, then there is a differential amount of mass flow rate which is coming here. Depending on whichever is greater, there can be accumulation. Similarly, there can be accumulation because V at y and V at delta y, y plus delta y are different, or W at z and W at z plus delta z are different. So, this is the total mass flow rate going out and this total that is coming in, and you can write a mathematical expression dou by dou t of rho delta x delta y delta z equal to all that is coming in minus all that is going out. So, we can now do some simple manipulations. We can divide this whole thing by delta x delta y delta z, the product, the volume, and then take the limit as delta x tends to 0, delta y tends to 0 and delta z tends to 0, because we are looking at equations which describe change at every point. So, we are looking at a control volume with a volume of a point. Of course, point has no volume and we cannot conceive of particles having no volume. So, this is the, when we say delta x tending to 0, we are looking at so small that it is practically like a point when we look at our applications, but mathematically it is still large enough that we can think of billions of particles which are present, so that we can talk about average properties and all that. So, that is known as the continuum hypothesis. So, within that 0 is defined subject to the continuum hypothesis. So, if you do this, then the left hand side becomes dou by dou t of rho, because this thing cancels out, and if you look at these two delta y delta z cancel out, this gives you rho u at x minus rho u at x plus delta x divided by delta x, and if you take the limit as delta x tends to 0, this becomes dou by dou x of rho u. So, these two together will give you minus dou by dou x of rho u, these two together will give you minus dou by dou y of rho v, and these two together will give you minus dou by dou z of rho w. So, if you, these are all minus, so you bring it to this side and then you have this form here, which is the conservation of mass. So, dou rho by dou t plus dou by dou x of rho u plus dou by dou y of rho v plus dou by dou z of rho w equal to 0, or delta rho d rho by dt plus d by dx I of rho u I equal to 0 is the index notation. So, this is the statement, mathematical statement of the conservation of mass. So, in the next lecture we look at how to derive an equivalent mathematical expression for the conservation of linear momentum and all that.